In this video, we're going to talk about motion analysis of slider cranks. So this is similar to the motion analysis, so that's position, velocity, and acceleration for 4-bar links. But we're going to focus here on the slider crank mechanism. So here is a diagram of the slider crank mechanism. In this diagram, we are defining the nomenclature for it. So what you'll see here is we've got R2, so that's vector 2, and the length of vector 2 is A. We've got vector 3, and the length of vector 3 is B. And those are fixed lengths, those are known. We've got vector 1, and then vector 4, and the length of vector 4 is known. So A, B, and C are known. We've got our angles measured from the tail of the vector, so theta 2 counterclockwise. From the tail of the vector, we've got theta 3 running counterclockwise, and then we've got theta 4 running counterclockwise. In this example, vector 1 is interesting. So what we know about vector 1 is the angle of vector 1 is 0. We have aligned it with the x-coordinate system. What's interesting about this is that the length of vector 1 changes. Okay, so the length of link 1 changes. So you can imagine if we're rotating our crank around counterclockwise this way, the length of link 2 and the length of link 3 does not change. This will oscillate to the left and the right. The distance between x and this x-coordinate system will remain the same, but what changes is the distance from this origin to length to B, to point B. Okay? This is what we're calling an offset slider crank. Okay, it's offset because R4 has a value C. We're going to derive these expressions for when R4 has a positive integer value, C, some length, but you can imagine that if C is equal to 0, then this link slides along the same line as this origin. So with this diagram, we can write up the x and y components for the positions of this vector. So vector 2 is A cosine theta 2, A sine of theta 2. That's going to tell us where this vector is pointing. R3 is B cosine theta 3, B sine theta 3. R4, C cosine theta 4, C sine theta 4, and R1 is D cosine theta 1, D sine theta 1. And the vector loop for this, if we start at the origin, is going to be R2 minus R3 minus R4 plus R1 equals 0, right? So this is the vector loop equation for this slider crank. So we've got, again, the x and the y components. We put into our vector loop expression, which we derived previous, and we can collect those x and y components. So our x expression and our y expression are given here. We know some things. So here are the things that we know. In this case, we know that vector 1 is aligned with the x-axis, so theta is 0. The other thing that we know is that theta 4 is 90 degrees. So we can simplify our expression. When we simplify our expression, what we end up with is A cosine theta 2 minus B cosine theta 3 minus D is equal 0. And the y component is a sine of theta 2 plus b sine of theta 3 minus c is equal 0. So these two expressions now we can solve simultaneously. And when we do, we get the following solutions. So the first thing we get is we get a value for theta 3, 1 and a value for theta 3, 2. What you'll notice is there's a 180-degree difference between the two. The other thing that we solve for, the other value that we solve for, is the length of d. Now, if you remember right, our expression or our diagram looks something like two, 3, 4, 5, 1. Okay. So we are solving for this length d. That will tell us how far this point B is away from this origin 2. Okay. So we can solve for these things. Well, for these values. So we have theta 3. Here's theta 3. Okay, and d. So we can end up solving for these. Okay, so if you look here, we've got sine, arc sine of a sine theta 2 minus c over b. We know c, we know b, it's given to us. We know a. Theta 2 is an input to the system. So if we know that, we can solve for this value of theta 3, 1, and similarly down here. Once we solve for theta 3, 1, we can plug that value in here. Again, now we know b, we know a, we know theta 2. We can solve for d. Okay? So this is the general expression for slider crank. Okay. Now, here is a simplified version of the diagram that you see. R2, R3, R4, and R1. If this is an inline slider crank, that point moves down, R4 goes to 0, and R3 is solved something along these lines. So if we go back here, then what we see is this expression still works, right? This expression still works. Essentially, c, or the value of c, is 0. So these are the equations that you can put into an Excel or a MATLAB code and get position analysis for a slider crank mechanism. If there are any questions, please post them to the discussion board, and I will answer them for you.